Very good morning. Today we will talk about the properties of mutual information. If at all we go for the properties, so the properties as we just now mentioned, that is where the both are reciprocal, which are equal, I x comma y equal to I y comma x. Anyway, that is reciprocal. And now as we know the entropy average information of about x and conditional entropy x at y, okay, after observing the output, before observing the output, the uncertainty about the input channel and difference between these is while observing the output, the uncertainty about the x input, the mutual information, we just simply simplify and we get the mutual information, the expression of like this. Just we go through this. See, this is where h of x sigma p of xj logarithmic base to 1 by p of xj for all j. This is the entropy of input probabilities of p of xj. Okay. And this is equal to where taking it as simplifying, we are expressing this h of x in terms of converting into joint probability. Just by multiplying this sum of all the transitional probabilities for all k here, which is equal to 1. So just by multiplying with 1, there is no change in value. So this h of x is multiplied with 1 and this is becoming a whole expression can be termed as sigma j equal to j minus 1, k equal to k equal to 0 to k minus 1. So this p of x is p of yk at xj into p of xj and logarithmic base to 1 by p of xj. As you know, this is what just now the product is a giant probability, and this is termed as giant probability and logarithmic base to 1 by p of x. So this h of x is either here we define or h of x in terms of giant probability, this both the variables between input and output j equal to j minus 1, k equal to 0 to k minus 1 in terms of giant probability. As we know that input probability is p of xj, it is simplified and defined in this fashion. The same way, you also take the conditional entropy h x at y. As per the definition, the x at y, so that is what x probability p of x at y. So that is being taken p of x j at y k, and you multiply with again the sum of the all the probabilities of p of y k, just that the product is becoming again the giant probability. So this is what the giant probability. If you take this minus this, the common, the p of x comma yk multiplied with logarithmic base 2. So this is where the minus of this term, it is getting a numerator because of logarithmic property. And already this p of xj, it is there in the denominator. So p of xj, you can add because of this logarithmic two terms of this and this, then because this is a minus of value, it becomes reverse. So this is what p of x at yk divided by p of x. So the mutual information finally it is defined I x comma y is like this. Knowing the giant probability and the conditional probability and input probabilities, that can be estimated mutual information. Okay, the same thing if you want to express the I x comma y as I y comma x, which is same, reversible as per the definition, the Bayes principle. So P of xj at yk by P of xj is nothing but P of yk at xj by P of yk. This is the probability theory mathematical, the Bayes rule. Okay, and then in this case, P of xj at yk by P of xj can be replaced P of yk at xj by P of yk. So the summation of these joint probability logarithmic base to P of yk at xj by P of yk is nothing but it is a y comma x I of y comma x. So that is how. So then I of x comma y is nothing but I of y comma x. That is the mutual information. The principle, the property, first symmetric is proved. So next property, if you go to the next property, this is always positive. Mutual information never be negative. Never be negative. It is always positive. As the definition summation of sigma j and k, P of xj at yk, that is giant probability logarithmic xj at yk, P of xj at yk by P of xj. This is what the definition I of x comma y. Okay. So P of xj in this giant probability, because P of xj at yk multiplied with P of yk is a giant probability that is being replaced here. So then P of xj at yk by P of yk. So this product again and the individual probabilities. And this is where giant probability, you have. And there are giant input probabilities and output probabilities and transitional probabilities. There is no loss of information by observing the channel output. So always the information will be positive. So we'll go to third property. We have one more property. Mutual information can be expressed summation of average information of input x, average information output y, minus of that giant entropy of the x and y. So that is what the definition. So that it is related with the giant entropy of the channel. So here, if you take the giant entropy H, the definition of the average, that is entropy, is same sigma of probability, sigma of probability, and the logarithmic base to 1 by probability. Okay. So that is where that is giant probability of x comma y. You will have two summations of j and k, so that this is the giant probability. So the h x comma y summation of sigma j equal to 0 to j minus 1, k equal to k minus 1, p of xj yk, that is the giant probability, and logarithmic base to 1 by giant probability. So if you know the giant probability, by the definition of the entropy, the average information is a summation of giant probability multiplied with logarithmic base to 1 by probability. So that is what the giant entropy. The same way in the entropy definition. If you take this giant entropy, we can further simplify, which can make equal to find out what is the mutual information in terms of h of x plus h of y minus of h of x comma y. So I'm taking this third term, like this is the h of x comma y. By the definition, this is the expression. So we are further simplifying just mathematical manipulation without any loss of generality. So without losing any value, and this summation p of xa comma yk logarithmic base to 1 by p of xa at yk, and we are adding logarithmic base to p of xa and p of yk. So in this logarithmic principle, if you add in the numerator, you can subtract in the denominator. That means you add and subtract one. While subtracting, you will get the denominator term. So that is what, so this is where we are splitting into two terms. This is first term and this is second term. Just by adding this numerator and again denominator, just subtracting here, that is what it is cancelling out in the logarithmic principle. And there is no change in that value. Okay. Now, because the joint probability is nothing but, as we have just seen, the product of p of xj at yk multiplied with p of yk. Okay, you can also take p of xj at yk is nothing but p of yk at xj into p of xj. So that is the base rule, and we got the same. So xj at yk into p of yk, or yk at xj into p of xj. That is also right. So now, if you substitute this p of xj at yk into yk, see p of xj at yk into yk, p of yk gets cancelled here, and p of xj by p of xj at yk. So this first expression, p of xj at yk, logarithmic base to p of xj by p of xj at yk. See, just now we have seen that mutual information in terms of joint probability, sigma double summation p of xj at yk logarithmic base to p of xj at yk by p of xj just now. So this is inversed. So inversed means logarithmic 1 by logarithmic means minus of that. So this is nothing but minus of mutual information. This first term. Now we'll see the second term, this one as p of xj at p of yk. Again, further split into two terms so that the second term you take this, further simplify into two terms. So this is what one term, this is another term, adding the logarithmic value. So here split into two terms again because of p of 1 by p of xj, p of yk. Logarithmic base to this term, we are adding separated into two terms. So now, out of which, by manipulating sigma j equal to j minus 1 logarithmic base to 1 by p of xj, anyway, the rest of the term sigma k equal to 0 to k minus 1 of p of xj comma yk. So what is the joint probability sum k equal to 0 to k minus 1 for every input of x? This is what input probability. Sum of all these giant probabilities for all the range of k for every given x j. This is the p of xj you get. So this is what p of xj. As you know that p of xj into logarithmic base to 1 by p of xj. So this is what p of xj logarithmic base to p of xj. So this is what h of x, average information entropy. Similarly, this term sigma k and p of logarithmic base to 1 by p of yk, and rest of the term sigma j equal to j 0 to j minus 1 of joint probability, this one, sum of all joint probabilities for the all range of j for a given every yk. So that is what we get yk. So this is what p of yk. So this is what p of yk. So this p of yk is taken as substituted here. So sigma k equal to 0 to k minus 1, p of yk logarithmic base to 1 by p of yk. So this is other nothing but entropy of y, output y. This is entropy of input x, xj. So for all j, this is for all k. So this is sum of h of x plus h of y. This is what second term. And joint entropy in the first term, we got minus of that mutual information. This is the first term. And this second term is nothing but h of x plus h of y. So this is what now ultimately that mutual information is h of x plus h of y minus h of x comma y. So this is what joint entropy and entropy of input, entropy of output. So this is what the mutual information of third property. If you know these probabilities, you can find out the entropy of individual, whatever the probabilities are given. So accordingly, the mutual information can be estimated.